All right, so let me go into this continuation about OpenCL programming. I will not introduce all three examples. I spent most of the time will be on the MapReduce example. Okay. We talked about the general concept or strategies of doing decompositions. Decomposition refers to the fact that we want to partition a big problem into smaller ones so that we can address them individually. Depends on the properties of the problems or the underlying hardware limitations. A quick review show you here that we basically have two ways of considering the decompositions, and these two strategies are not exclusive. First one is divide and conquer. Essentially, we want to iteratively break a problem into sub-problems, and we could do this many times until the sub-problem can fit into the computation resource provided. The other strategy is to do scatter and gather. In this category of approaches, we send a subset of the input data sets to those parallel resources. But because the final result depends on a integration of the results from these subproblems, so inherently we will have to do kind of in two passes or two stages. One is to scatter. That means you're gonna distribute all these different smaller problems into your computer units or processing element, whatever underlying hardware that you carry out these subtasks, sub-problems. And after they complete these smaller problems, we'll then collect the results back. We not necessarily simply collect. We actually, in many cases, we have to do additional computation on those results from these smaller problems. And then we collect and then combine them into the final result. So MapReduce is basically in the second category, where we want to partition the bigger problem into smaller problems, sub-problems, and address them individually. This is the mapping phase. And then on the second stage, the so-called reduction phase, we'll collect results from the first stage, combine them, not necessarily simply combine, we may do additional computation, but on top of these results, we will form or deliver the final result. This idea was first proposed in a 2004 paper from Google. It's called MapReduce Simplified Data Processing on Large Clusters. And Google has been dealing with these large-scale problems. Search engine is, of course, its root, and that's a huge problem. On the internet, there are billions of web pages that they have to visit and to process these links within each individual web pages and build a complex web link graph. And also they will look at these keywords in these web pages and be able to index them. So next time when you putting a keyword in the search engine, Google can return the relevant web pages to you in sub-seconds. So the reason they have this MapReduce is they have this very large scale problem on one hand. On the other hand, they have a lot of computers. And these computers are there in their data centers serving all these different web pages or answering these different queries. So they need a method for processing these large data sets and using these large number of computers and processors. And they want to have a general approach that can be applied in multiple applications. And I will give you some examples. And this MapReduce approach, as I mentioned earlier, has two stages, mapping and reduction. And so we're going to use these two words throughout this lecture. First stage, mapping. Mapping is to basically give these large number of processors some work to do. These processors will receive data as an input and produce a result. And this result is what we call key value pair. So it's not just a random result. There's a way to organize them, and that the way to organize them is to use these key value pairs. We'll show you an example. The key basically is a unique identifier. Could be a number, could be a string, could be a URL. As long as it can be uniquely identified, that can be used as a key. And value could be different type of data. Could be numbers, could be a string, could be a list. So that depends on the application. Once these large number of computers and processors finish the initial computation, they will produce this key value pair. So key value pairs will be coming out from these different processors. And the second stage is so-called reduction stage. Processors receive and perform reduction on values corresponding to a given key. So the reduction stage could have also a large number of computers or processors. But these processors will be able to receive the key value pairs from the first stage, the mapping stage. And in the reduction stage, these processors will perform reduction on values. So the reduction could be very different, not really based on the application. It could be simply counting, so counting the number of keywords, or it could be some kind of sorting if you have a large number of jobs, or you want to provide sorting on the some metric. Or it could be building a graph, and that's the example we'll see in the web link relationship graph. The efficiency, so these are two stages, mapping stage and reduction stage. Now, why this is useful? Because it's efficient in operating the processors independently. Once you are able to partition the original problem into smaller subproblems, and then you can map them to these large number of processors. These processors are free to basically work on these subproblems and produce key value pair or key value pairs from their computation. And the same thing happens for the reduction processors. They can also work independently, and that's a big benefit for having these many processors or computers. It scales with the problem very well. So if you want to count the keywords in one chapter of the book, you can use it. You can do that on maybe, let's say, 10 processors. If you want to do the keyword counting for a whole book or 100 or hundreds of books, then you can scale the number of processors and be able to perform that processing efficiently. So let's look at this concrete example. So what we have here is some kind of input, and we have a problem as an input. This problem can logically be partitioned into smaller problems. Let's say we want to do some computation using these 6 blocks, and each block, imagine there are some keywords or data that the processors are going to process, and this input will be partitioned, and based on the number of processors. In this example, we have 6 processors, and we will perform this partition to divide the original input into 6 pieces. And typically these are equal sized pieces because you don't want one of the processors to get significantly more work to do than the other processors. And that will drag down the whole latency for completing the work. And that's you want the balanced workload on these processors. So these processors will be working on that problem, and then based on the actual algorithm or the application, some keyword pairs will be produced. So in this example, this M0 processor, working on the input data and produce 3 key value pairs. Now the key here is simply the number. So in this example, M0 produced 3 key value pairs, and the keys are 0, 2, and 3. The values will be, of course, different. Depends on the actual application. Similarly, the other processors will produce key value pairs. Now you can see that the number of key value pairs could be different from the mapping processors, simply because you don't know what actually data is going to be sent to these processors. And so if for some reason the input data from the original problem assigned to M1 does not have information related to key value 2, or keyword 2, then of course the output from the M1 will not have that key value pair. So when this mapping stage happens, all these 6 processors or computers are working at the same time. So you expect that these key value pairs will be produced almost the same time. And the next stage, after the key value pairs are generated, mapping stage will happen. In the mapping stage, essentially there will be another group of processors or computers will process these key value pairs. We have, in this example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 key value pairs produced from the mapping stage. We can do different kind of shuffling or different distribution strategies. Some of these key value pairs will be given to one processor, some other ones will be another processor. So there's some flexibility there. And you can use the hash values of these keys, or you can use other policies to distribute these key value pairs. In the reduction stage, on each of these processors, so we have 4 of them here, they will be combining these key value pairs. Now the combining could be, for example, what we're doing here is we send the key value pair. If the key is 0, we send that key value pair to R0. And if the key is 1, we're going to send the key value pairs to 1, and so on. So you have one reduction processor or computer that handles one keyword. So all the key value pairs will be put into or sent to this R1. And the R1 can use these key value pairs, for example, 1B here, 1B here, and 1B here. These could be different values. So then, but they have the same key. So R1 will be able to perform additional counting or building the list of links based on the single key word value of 1. And eventually, these reduction processes will output the result. So the final result will be keyword 0 counting counter value keyword 1 counter value, etc. 4 could be the list if you building a list for each of the keywords.